So, ladies and gentlemen, here we go again, now towards the black hole session. And we start with a presentation of one of our astronomy prize winners, Roger Blandford, a giant of astrophysics. And some cutting-edge expertise of Roger, black hole astrophysics, and the whole lot of compact objects, black holes, neutron stars, and white dwarfs. To that, cosmic rays and galaxies, gravitational lensing, and cosmology. Just a little about his career. Of course, as you can expect, truly exceptional, with a lot of very prestigious posts, and a long and very prestigious list of honors and awards. Not going to go through it, save the time for his presentation, but I just show you a lot of it that you get an impression. Rotating black holes. Many people may think that they are niches of physics, but they are very important bodies with very important properties. They are victims of their own gravity, and out of general relativity, they are probably the most fascinating consequence. At the same time as they are highly valuable keys to our real deep understanding of matter. We have the rapidly spinning stellar black holes, many of them. We have the supermassive black holes in the center of galaxies, in our own galaxy for one. For quite some time, observational data accumulated, but understanding did not accumulate very much. So the question was, how is the tremendous energy produced, and how are the jets generated, and how can these processes so energetic be maintained? There were many questions, but not many real answers until. So Roger Blandford, he commenced in-depth studies of theoretical models of the black holes to try to understand them, basing his work on the results of Roy Kerr, which we'll hear more about later. So it was, of course, a very difficult endeavor, even for Roger. Extreme gravitational forces, high rotational speeds, spinning magnetic fields, fluid dynamics, nuclear fission, and spiraling charged gas. Spectacular, but hard to get a grip on. So already one by one, all these things were very hard to understand, but together they were more or less insurmountable. Yet the models of Roger and his collaborators had simply amazing success, a smashing success, I should say. Gradually more refined and advanced, they provide us with sophisticated insight into the physics of black holes, so opening our understanding of what it was all about. A transformation of matter into energy and energy into radiation, extremely fundamental processes, of course. Energy loss and rotational speed, and then the exhaustion of gases and the following deceleration of processes. And we should not forget, of course, that the role of rotating black holes as test probes of our real in-depth understanding of astrophysics and the total world around us. They are key to much of this. And so, Roger, the floor is yours.
Thank you. A locomotive is moving. Someone asks, what moves it? A peasant says, the devil moves it. Another says, The locomotive moves because the wheels go around. A third asserts that the cause of this movement lies in the smoke, which the wind carries away. The peasant is irrefutable. He has devised a complete explanation. To refute him, someone would have to prove to him that there was no devil. The man who says that the movement of the wheels is the cause refutes himself. For having once begun to analyze, he ought to go on and explain further why the wheels go round, until he has reached the ultimate cause of the movement of the locomotive in the pressure of the steam in the boiler. He has no right to stop in his search for the cause. The man who explains the movement of the locomotive by the smoke that is carried back has noticed that the wheels do not supply an explanation, and has taken the first sign that occurs to him in his turn has offered that as an explanation. This passage, abridged from the epilogue to Leo Tolstoy's War and Peace, provides a fitting introduction to the story I want to tell you. I want to tell you something about some powerful cosmic locomotives called active galactic nuclei. They have wheels, they have smoke, and they can move impressively fast. In the century that has elapsed since we first observed these cosmic locomotives, astronomers came up with explanations that now seem strangely similar to those of Tolstoy's characters. Today we have some descriptions that are widely accepted as scientific fact, but they are not proven in the sense of Yasha Eliashberg, but they are supported by an abundance of observational evidence, some of which I will try to tell you about. But some of this story is less well supported, but it is provisionally accepted on the basis of observation and physics. And finally, some of my lecture will discuss some exciting conjectures that await confirmation or refutation. This is the way of science, which is, after all, a progressive activity. However, before I start this story, I want to say how honored and yet how humbled I am to be awarded a Crafoord Prize in Astronomy. I am deeply grateful to Royal Swedish Academy, the Crafoord Foundation, and the Crafoord family who I had the pleasure of meeting last night, and especially to the memory of Holger and Anna-Greta Crafoord for this wonderful recognition. I thank you all so much. My story begins over a century ago, when Edward Fath, a graduate student at Lick Observatory in California, observed a small nebula, then called NGC 1068, and he found that it had a bright nucleus, with lots of spectroscopic emission lines. And this is just a graph here of how much light comes out as a function of the wavelength of the light, going from the blue on that end to the red on that end. This is a spectrum. This was the first example of an active galactic nucleus, although it was not known at this time that these nebulae were in fact galaxies, collections of billions of stars distinct from our own. NGC 1068 is a Type II Seyfert galaxy named after Carl Seyfert, who studied them. Whoops, sorry. Go back. There we go. Whoops. So I've got there we've got it. There we've got it. Okay. Carl Seyfert, who studied them in 1943. Now, if you're beginning to suspect that active galactic nuclei are classified in a manner that would make your most famous alumnus, Carl Linnaeus, weep, you'd be right. Astronomers do not even use Latin for these purposes. We are truly hopeless. However, we think we understand how to look at them, and they are in many ways like people, all rather different, rather than like elementary particles, which are all the same. A decade after Fath, Heber Curtis, again working at the Lick Observatory in California, observed another galaxy. This time it was an elliptical galaxy, not a spiral galaxy like NGC 1068. And its name is M87. Curtis was a careful observer and noticed what he called a curious straight ray, which you can just see if you look very carefully in this modern photograph. This is a photograph, not a CCD image, but it is made with a modern camera. And you can just see this ray there. And he noticed this, and he noticed the brightest end was at the center of the galaxy. You can see this feature now there in the blow-up there. It's just about visible there. And this is the first example of what we now call a jet. Now fast forward to 1953. The infant science of radio astronomy, which had been developed towards the end of the Second World War, was starting to find sources outside our galaxy. One of these was associated with a quite distant galaxy called Cygnus A. At the time, it was thought that this might be two galaxies in collision. So imagine the surprise when one of the radio astronomers, two of the radio astronomers known as Jennison and Dasgupta, and you can see them there, demonstrated that the radio source comprised two regions of emission straddling the galaxy. There was one of the radio emissions. This was the first image that was made using radio telescopes, and there's the other one there, and here's the galaxy in the middle. So on either side is where the radio emission was found. And this was the first example of another common type of active galactic nucleus known as the double radio source. Now advance another decade to 1963. A large number of these bright radio sources had been discovered, and a radio astronomer, Cyril Hazard, up there, used the moon to find a precise position for one of these. Its name was 3C273. An optical astronomer, Martin Schmidt, up there, found its optical counterpart, and he took a spectrum which indicated that it was a very long way away. He was able to conclude that the light from 3C273, this first example of this type of object, was 100 times more luminous than a galaxy. In addition, though, it appeared to be small, and it looked like a star, so it was called a quasi-stellar object, or a quasar for short. 3C273 also had a jet. Now, our understanding of active galactic nuclei has developed considerably since these early discoveries. And I just want to encapsulate this in a few propositions which I'll illustrate and then return to this list again. We now know that essentially all galaxies have nuclei, which exhibit some activity. That's the first proposition. We also know that nuclei radiate throughout the spectrum, from the lowest energy radio waves to the highest energy gamma rays. We know that the nuclei can vary very rapidly and must be very tiny, like an atomic nucleus inside an atom. And they have central cores no bigger than the solar system in this giant galaxy of stars. We can also measure the masses of these central objects, and they range from 1 million to 10 billion times the mass of the Sun. And we can do spectroscopy, not just in optical wavelengths like Mr. Fath, but we can do this all the way throughout the spectrum, and especially at X-ray energies. A further proposition is that these objects, with modern language, have an intense environmental impact. They affect the regions all around them. And finally, the jets, which will be a large part of the rest of this talk, they comprise material flowing outward close to the speed of light. So I'll now try and illustrate some of these propositions, and then we'll return to this point, this list again at the end, just to try and refresh your memory. So, firstly, the nuclei. Here is 3C273. I said it was quasi-stellar. So what astronomers can do now is block out the light from that very small point at the center and look around it. And what they see is a galaxy. You can see it here. This is done with Hubble Space Telescope. And it is clear that there is a normal galaxy with very, very bright nucleus in the middle of it. Here is our galactic nucleus. You don't have to be a great astronomical scholar to guess where the center of it is. Of course, it's there. But we see this spiral structure here. It is almost certainly gas that is falling in towards it. All right, so there's the center of our galaxy. Let's go on to this second proposition, that nuclei radiate throughout the electromagnetic spectrum. So here is the electromagnetic spectrum as seen by an astronomer. It extends in wavelength all the way from the lowest radio frequencies to the highest energy gamma rays, right up there. And if we think about what we can see with our eyes, it is essentially just one octave of frequency or wavelength. Just one octave on the piano, for example. And if we imagine the whole spectrum spread out, there would be 10-gram pianos worth there, 70 octaves of electromagnetic spectrum, and astronomers have access to more or less all of this. Here is a low-frequency facility. It is part of a European consortium called LOFAR, and it happens to be located up the Swedish coast at Onsala Observatory. And they look at sources using the lowest radio frequencies, and there is an image of M87. Remember I said M87 was that elliptical galaxy? This is what it looks like at the lowest radio frequencies, and Onsala participated in this observation. By contrast, if we look at gamma rays, here's Fermi Gamma Ray Space Telescope, an orbiting gamma ray telescope, and here is what the center of our galaxy looks like. So this is looking at the whole of the sky, and we just wrap it around. We unwrap the sky, and then project it onto an almost elliptical-like shape like this. Here is the center of our galaxy, and we see these giant bubbles coming out from the center of our galaxy. Those bubbles are made by the active galactic nucleus in the middle of our galaxy. However, it is not particularly active now. It is quite dormant. Do not be ashamed of our galaxy. You would not like to live too close to an active galaxy. So I said that active galactic nuclei are very small. Here is some evidence. This is another quasar. I won't bother you with its name. And here is the gamma ray intensity that is measured from this quasar, measured in minutes. Okay? And what we see is that there are variations in the gamma rays that come from this quasar on timescales that can be as short as a few minutes. 2 minutes or so is the record, I think. And remember, it takes light 8 minutes to get from the sun to us. So that tells you it has to be very, very compact. Now let's talk about the masses of these objects. Here is M87. What we can do in M87 is measure the speed of gas that is in orbit around the central object. We can also measure the size of that orbit, just like we do with the solar system. And in that way, we can figure out the mass of the central core that's responsible for all of this activity. And it turns out to be 6 billion suns. Now, I have to qualify that. Some astronomers say, no, it is not 6 billion suns. It is 7 billion suns. And some say it is 4.5 billion suns. And there is a vigorous debate, but the debate is so narrow, tells you how much this subject has improved. Here are the last two Crafoord Astronomy Laureates, Reinhard Genzel and Andrea Ghez, and they were recognized for a remarkable observational tour de force, which is carrying out the same trick in our galaxy. And here we don't use gas, they use stars, and they trace the orbits in infrared wavelengths of stars orbiting the center of our galaxy. And with luck, are the orbits of those stars shown at infrared wavelengths, and you can see complete orbits there, and that way you get a very precise measurement of the mass of the central object, which is 4 million solar masses. Let us look at the spectra. So here's a spectrum of 3C273, our first quasar. We know of thousands of these things, of course, now, but I'm just taking a few examples. This is 3C273 again, and we see bright lines, and we can learn about the elements that are in it and a lot about its properties. Here's a spectrum here of NGC 1068. That was that Spherical galaxy, the very first one I showed you. Again, what we're looking at here is the amount of light as a function of the wavelength. So we're looking at a graph of the amount of light versus wavelength, and each of these lines here, just like in the spectrum of the sun, corresponds to a different element or a different ion. And so we can learn about the composition of these objects and a lot about the physics of what's going on there. Here is an X-ray spectrum, and this is one, if I get time, I will explain a bit more about, and this is a line of the element iron at an energy, which we say is 7 keV, because X-ray astronomers like to talk about energies, and we see shape of the line there, and I'll come back to that point a little bit later. So remember that X-ray spectrum in fact, that's of another Spherical galaxy. So, another proposition I made was these active nuclei have a big impact on their surroundings. Here is the Virgo cluster, and this is M87 in the middle of the Virgo cluster. This is what it looks like at X-ray wavelengths, and that is a lot of hot gas. M87 is a small feature in the middle of that. This is all this hot gas at temperatures of over 10,000 times the temperature of the sun, and it has to be heated. And we believe that it is the tiny object at the center of this M87 galaxy here. This is the LOFAR image again. That is causing this gas to stay hot and to radiate. So it is heating this gas all around it. So it is very powerful, the object at the center of the M87 galaxy. Let's turn to my favorite subject, which is the jets. We've already seen the jet in M87 that was discovered by Curtis. This is what it looks like at X-ray wavelengths. There are many other images I could show you here, but I'll just show you one made with an X-ray telescope called Chandra X-ray Observatory. Here's what it looks like at radio wavelengths. And here's a technique that is used by radio astronomers called very long baseline interferometry. And if you want to see fine structure in these galaxies, then what you do is put radio telescopes in different places, often in different continents, and combine the signals from these different radio telescopes. And that is like looking at the sky with a telescope that is as big as the Earth. And so we get very good resolution, very good fine detail on the images of these galaxies. So here is a European VLBI network. You can see that observatory up there. That's Onsala. So you can see it's part of this large consortium, including famous European places over here. And That's what it can produce. And we are looking down on the jet of M87, and this is on the finest scale, and it turns out that we're looking very close to the putative size of the central object that is responsible for all of this power and all of this activity and for these amazing jets. Here's what it looks like using another very long baseline interferometry experiment. This is a map. It was a movie, and I won't be able to show it to you here. It looks like. So this is this movie of variations in this jet, and we can see a jet coming out of the nucleus of the galaxy there, and it is bright on the edges, which is significant, and again it extends out to way out into the other side of this complex here. This is looking on the very finest scale here. This is milliarc second. This is a dime in the United States, seen from here. Here's the jets in Cygnus A. Remember, that was the first image in 1953, made by Jennison and Dasgupta in Manchester in England. This is what it looked like using the Very Large Array in New Mexico. There is the galaxy there. There is the nucleus of the galaxy. You can see this jet coming out here and powering these large lobes of radio emission. These are radio images. Another one you can just see powering the lobe on the other side there. So here are the giant lobes of radio emission powered by the nucleus of the galaxy. This is what it looks like with VLBI on very much smaller scale, just from the center there. There's the nucleus of the galaxy, and here we can see the jets. Just like a Matryoshka doll, we take it apart and you see another Matryoshka doll inside. (3C273). Here's a very old experiment. This is an image made in 1977. There's one made in 1979. And there's one made in 1980. We can see this feature here moving outwards relative to the core there. We know how far away it is. Therefore, we can see how fast it is moving. It is moving at approximately 8 times the speed of light. Now, some of you who know special relativity may be disturbed by that because you may have heard that nothing could travel faster than the speed of light, except possibly a rumor, and that carries no information, so there is no physics violation there. However, it is not a real motion, it is an illusion. So if you imagine, over there at the back, that you are the observer, and this is the center of the galaxy, and this is a moving feature, and if it moves almost at the speed of light, like that, then it will appear to you to move faster than the speed of light. It's just an illusion. Anybody have any questions they want to ask on what we've talked about so far? Yes, a question. Excellent.
Roger, I was wondering, what's it like to live in an alien galaxy?
Oh, what's it like to live in an alien galaxy? In a quasar, you would not want to be there. The irradiation of the cosmic rays and the gamma rays and the X-rays would make the mutation rate something splendid to behold. You would not last very long in that environment, I can assure you, even at the distance of the solar orbit. So, our galaxy in the past almost certainly was much more active than it is today, and it was never a very powerful galactic nucleus, but it would have had if it were a Spherical galaxy, it would have had environmental impact, I think. So that's a good question. I don't blame this killing the dinosaurs, though. Yes. Okay, here we go. Okay, so we're back now. Okay, let's hope that all goes well. So anyway, let's take stock of these observations. This is my checklist again, and just to summarize, active galactic nuclei are common, and they are compact. They are powerful, and they strongly infect their environments, and they are massive and cause gas and jets to move with speeds close to the speed of light. That's a lot of circumstantial evidence. And of course, as I'm sure almost everyone here knows, that we now believe that all of these amazing properties are caused by the structure whose name I have not yet spoken, and that is the locomotive. And the locomotive, is believed to be a massive black hole in the galactic nucleus. We require this to explain the prodigious power and the tiny size. And in fact, it was one of the first suggestions that was made in the years after quasars were discovered in 1963, but it took nearly 20 years, I think, for this notion to get full acceptance. Now, a black hole by itself, and you'll hear much more about these, I should say, this afternoon from my colleague Roy Kerr, but a black hole itself will be pretty dormant. In order for it to become active, like the many examples I've showed you, it requires gas to fall onto it, and it will form a disk. Now, I have here a model of a disk. So here's a disk. I don't know if anybody can see that. And no expense has been spared in this demonstration. So here is the black hole in the middle, and the disk will orbit around it, like that. Now, you got that point, very difficult. Now, there's something slightly subtle about this, and I'll come back to this point in a moment. Because this is like the planets orbiting the sun, the gas in the middle of the disk will travel faster at a faster angular rate than the gas on the outside of the disk. So this ring in the middle here, if you can see that ring there, that ring in the middle will orbit faster. And so these radial lines here will become twisted like that. They'll make it more like spiral patterns after a short period of time. And that'll be important for something I have to say later. Now, why does the gas falling down in this disk, what happens to it? Well, it turns out there's a sort of magnetic friction in that accretion disk. And that magnetic friction, this is a cartoon, of course, that magnetic friction heats the gas. If you just imagine rubbing your hands together, they will get warm, and that friction will heat the gas. And that gas glows, and it radiates ultraviolet radiation and X-ray radiation. And that's how we see these quasars and the other active galactic nuclei I have mentioned. So if we think about this in terms of Tolstoy's locomotive, this is perhaps the steam in the boiler. Ultimately, of course, it is gravity that is powering this action, because just like a satellite in the atmosphere of our Earth, this gas will, and the action of friction, will spiral inwards, releasing its gravitational energy, and that'll be the source of the energy for the radiation that we see from across the universe and that outshines the host galaxy. However, this doesn't account for everything that we see. In particular, it does not account for the extremities of that electromagnetic spectrum. It does not really account for the radio emission and the gamma rays, for example. And for this, I think we have to appeal to a different sort of locomotive here, and this is an electrical locomotive. And this, we believe, is responsible for a lot of the non-thermal activity, including especially the jets. Now, the keen-eyed amongst you may notice that this is an American railroad. However, you should also notice with pride that this is a Swedish locomotive. So I'm going to try and explain to you a little bit about gravity now and electromagnetism. So this is going to be an awful lot of physics very, very fast. Gravity. This is Woolsthorpe Manor in Lincolnshire in England. It is where Isaac Newton was born and where he formulated the law of gravity and invented calculus. The mathematicians here may notice the integral signs that he carved into the wall there. The mathematician historians may notice this as a cruel joke because it was his bitter rival Leibniz who invented the integral sign. At any rate, I was born very close to Woolsthorpe, and I boast about this to my students. They are not at all impressed. A well-known myth is that Newton watched an apple fall from a tree and realized that the fall of the apple could be described by the same agency as that responsible for the orbit of the moon. And he invoked an invisible gravitational force to do the job. And he also formulated the mathematics that was needed to make these ideas usable. Here are his laws of motion and gravity expressed in the form of mathematics. There's a force there, an invisible force, and it causes an acceleration. Now jump forward 250 years to 1915 when Albert Einstein formulated his general theory of relativity. There's Einstein. He combined his three-dimensional space with time, or three-dimensional space with time, I should say, into a more four-dimensional space called space-time, a single entity, and he discovered that this space-time was curved in the presence of matter. He did away with Newton's invisible force and said the motion of the apple or the moon was essentially a straight line in this curved space-time. Here is Einstein. So this is, if you like, a depiction of the curved space-time around the Earth. Imagine things get a little bit distorted by that, and then an orbiting satellite, like the moon, for example, will follow what it thinks is of as a straight line in that curved space-time. Now, here is his equation, which supplants Newton's equation, and what it really means is that curvature is given by matter. So the amount of matter and stuff like matter, or energy around, if you like, in a slightly more complicated way than this, is responsible for the curvature, and there is that identity. And that, in simple language, is the content of Einstein's general theory of relativity, and it appears to be correct to about 10 parts per million within the solar system. We have no real grounds for doubting it as far as it can be used. So if we start talking about black holes, here is the sun with the warped space-time around it, and there is a black hole with the deeply warped space-time, strongly warped space-time. And here is Karl Schwarzschild, who was an observatory director and a German soldier in the First World War, and he discovered soon after Einstein published his equations a strange solution to Einstein's equations. And today we know that this describes a black hole that is not spinning, it is just spherically symmetric. And in particular, today we know that it contains, if you like, a surface. We can think about it as a two-dimensional surface, but that's not quite correct. And that surface is an event horizon. We call it an event horizon, and we can just think about that as a surface of no return. If you cross that surface, that event horizon, you cannot get out, at least by classical processes. Now, this idea had occurred to an earlier English scientist called John Mitchell, on the basis of Newtonian approach. And so in some ways, he might have been the first person to think about this. He said if we made the sun sufficiently compact, it would get to the point where not even light could escape it. So there was some precedent for this idea, but Schwarzschild did something very impressive mathematically, given the novelty of Einstein's equations. Now, if we talk about the more recent discoveries of black holes, there was a confusion for many, many years. If we were to watch a star collapse to form a black hole from a safe distance, it would take an infinite time for this to happen. And many scientists, including Einstein, who got rather confused on this point, said that black holes should never form. Now, this argument is not terribly helpful or useful, and this was, the fallacy, if you like, was exposed by John Wheeler and his colleagues about 50 years ago. And they pointed out correctly that if you were sitting on unfortunate enough to be sitting on the surface of the collapsing star, you would fall in finite time, in less than a millisecond, say, for a star like the sun. And the collapse would continue until gravity got stronger and stronger, and the laws of physics as we understand them would break down. Now, he coined the phrase black hole, although he didn't actually introduce it. He didn't coin the phrase black hole, but he did introduce it. And my title is essentially a nod to his essay written in 1965, called Introducing the Black Hole, which did a lot to making black holes respectable within physics and realizing that they were also very important and likely to be very important in astronomy. Following this, this decade in 1960s, I should say, was the golden decade of black hole physics, before my time, but not before Roy Kerr's time. And in 1963, as you'll hear this afternoon, he made a stunning discovery of the rotating black hole solution. So there's Roy Kerr. Okay, we'll see a better picture of him this afternoon. And he made, this is a truly amazing discovery. And very soon afterwards, things were discovered by Roger Penrose and by Stephen Hawking and many others working very fast, who realized that the solution that Roy found was really the solution for astrophysics. There are other figments of the febrile imaginations of theoretical physicists which we can discuss, and they are of genuine interest, but as far as astronomers are concerned, the simple solution, not so simple solution, but the solution that Roy found is the one that we will need. And what was also shown was two very important things. Was something called the area of the black hole could not decrease, and we now think about that as physicists as a form of entropy. And the other thing that Roger Penrose showed in a sort of thought experiment was that if you had a spinning black hole and you were to form an experiment and to throw rocks into it in a special way just outside the black hole, so you're outside the event horizon, you weren't lost forever, you threw rocks into it in a special way, those rocks could be on orbits with negative total energy, including their rest mass. So deconstructing that slightly confusing sentence, what it means is we have in principle a mechanism for taking energy out of a black hole. So by classical processes, we can take energy out of a black hole using, in his example, using rocks, and you had to be very close to it, and you had to throw them in, but that proved that there was energy that was extractable from the spin of the black hole. In fact, these two results together prove that. Now, as I said, this idea was discussed in 1964 as far as the active galactic nuclei are concerned, but it was with the stellar black holes that the first really strong evidence that they existed came, and this came from objects like Cygnus X1, which is a binary X-ray source. This is a regular massive star, shown here in blue, and here it is losing mass and forming an accretion disk around the black hole there, and we can measure the mass of that black hole, and we found that it was so large that the only alternative was for it to be a black hole. It couldn't be a neutron star or one of the other candidates. So this was, in fact, the first really strong evidence that black holes actually existed in the universe rather than as theoretical possibilities. We now know of many other examples of black holes, in particular gamma ray bursts, which are flashes of gamma rays lasting often less than a second, seen right across the universe, are now pretty convincingly associated with the birth of black holes, seen inside seen in most cases inside a massive star, and they too make big jets, and those big jets can move even faster than the HC associated with 3C273. So they are like very small-scale galactic nuclei, and they live fast and die young. So we see these gamma ray bursts essentially on a daily basis. So every day, more or less, we can see a black hole being formed somewhere in the universe. However, the most exciting development, very recently, has involved LIGO, the gravitational wave detector, and as I'm sure everyone in this room is aware, last September it observed the merger of two black holes with masses about 30 times the mass of the Sun, and they orbited together just these two black holes, losing energy by radiating gravitational radiation, gravitational waves. This was a type of radiation that was predicted first by Einstein, and this was detected by two very sensitive laser interferometers in the United States. And what they were able to do, these are so sensitive, these lasers, that they can see the motion, relative motion of mirrors like that, between which the laser light is bouncing backwards and forwards, and they can measure the relative motion, the positions of those lasers, by less than 1,000th of the size of a proton. Just think of that. Less than 1,000th of the size of the proton, they can measure the relative motion of those lasers. And using this technique, they observed a passing gravitational wave, and they were able to demonstrate that this was associated with two distant 30 solar mass black holes spiraling together like that, and they radiated the energy, if you say it's 230 solar masses, then let's say it's 230 solar masses, for example, then what they actually found at the end was 57 solar masses. The missing 3 solar masses was the energy that was radiated away. So this is E equals mc squared, one of the most famous equations in physics, on a grand scale. So 3 solar masses of energy was converted into gravitational radiation, and by the time it got to Earth, it was so weak that we had to measure the motion of 1,000th the size of a proton. Now, what's really, here's going to show you, here's a cartoon, here's the in-spiral there, there's the merger of the two black holes, the area, of course, must increase, according to Stephen Hawking, and then it'll ring down very, very fast. So you can think about this as some sort of diabolical dance, and the two dancers collapse exhausted at the end, going fast, they go faster and faster, and then they collapse exhausted at the end, just leaving this single black hole at the end. And this is the prediction of the general theory of relativity, and here is some data, and it fits astonishingly well. This is actual data from the two gravitational radiation telescopes, and it fits astonishingly well. And the fact that this was seen in the first week of operation means, and I happen to know this, there are a lot more of these on the way. So a whole new type of astronomy has opened up with gravitational radiation. So let me just summarize. These active galactic nuclei, the Spherical galaxies, the quasars, the radio galaxies, and so on, add through massive, tiny spinning black holes. The gas that falls onto them makes an accretion disk. It's heated, the gas in that disk is heated by friction, and it can produce the optical emission lines and so on. Now, the black holes themselves, a good question to ask at this point, given the next lecture, is are they spinning? And one of the things that we know is that, remember this X-ray spectrum here, this is one of the best pieces of evidence we have, is by measuring the shape of that spectral line, which is caused by gas in the disk reflecting X-rays. In fact, it turns out from a point above the axis here, we know that X-rays come from a point above the axis there, and that is reflected by gas in the disk. And by analyzing the shape of that line, we are able to show that most of these black holes are spinning very fast. So this is evidence that in nature, the black holes are going to need the full Kerr metric, not just some small perturbation of Schwarzschild's geometry. So let's move on. Okay, so this is one way that we see that, is that in fact it turns out that the center regions, there's an inner edge to the disk, which if the hole is not spinning is quite large, but the radius of the inner edge of the disk, if the hole is spinning, is quite small, and that's the way we tell that the hole has to be spinning very rapidly. Okay, so now let me move on. That was gravity and the black holes. Let's move on quickly to electromagnetism. And this is the final physics topic I need to discuss, and I want to discuss the subject of magnetohydrodynamics. It's known as MHD for a good reason, because magnetohydrodynamics is rather short and it's not got much to do with water. It's appropriate to do that here in Sweden because many of these ideas were developed by Hannes Alfvén, and I was fortunate to meet him on several occasions, and we always had very lively discussions. You're probably familiar with visualizing magnetic field lines using a magnet like this and putting some iron filings around it. So we have a big magnet like that and putting some iron filings around it. And so this was the way that Michael Faraday, one of my personal heroes here, thought about magnetic field. He thought about lines, say like that. That might be a line, and it might, whoops, oh. There we go. There we go. There's the, and so we thought about lines that might connect like that. And so he thought about the magnetic field in that way. And now, if we think about magnetic field lines, there are also electric field lines. And the electric field lines, unlike the magnetic field lines, will go from a positive charge to a negative charge. So there are electric field lines and magnetic field lines. And one of the things that Michael Faraday showed was that these electric and magnetic field lines were strongly interrelated. And for example, I can't perform this demonstration properly in front of you to show the electrical generation, but this is something called a Faraday disk. If I imagine this to be a conducting disk, like that, imagine it to be made of copper, not plastic, and then just spin it very rapidly like that, and then put some wires, one on the outside, one on the inside, and connect them to a light bulb. That light bulb would shine. This was an experiment that he formed in the 1820s, and it was the foundation of the sort of generation of electromagnetic fields and so on, and electric motors, and, well, here we go, yes. So, let's just move on. So we showed that these were very strongly related. Now, the magnetic field lines as we see them in astrophysics have very interesting properties. The first is the magnetic field, if we think about them in astrophysics, it will have pressure. So it will exert pressure like that. It will also, if you imagine this as a magnetic field line, it will also have tension. So it will have tension in it too. So we'll have a little demonstration here. I hope this is going to work. So my colleague here is, you're going to inflate it, and I'm going to do it. And if we try and combine the two, just a little bit, there we go. And we're going to try and put these on here like that. So this is the tension around the outside in these magnetic field lines, and then put another one like there. See if that works like that. And then another one there like that. And then maybe we can get one more on like that. And you're going to inflate them a little bit more, and I'm going to blow this up. So you see this? You see the difference? So the tension pulls it down and it changes the shape. Okay, so that works. Now, there's another important principle with magnetic field, and this is what Alfvén called the freezing in of magnetic field. And what he basically meant was that if you had a magnetic field line and some conducting gas, or some plasma as we called it, this is ionized gas, then the magnetic field lines would move with the gas. He called it the freezing in of magnetic field lines. Why a Swede would think of it in this way is completely beyond me. But I like to call it, as I come from California, the land of self-help books and so on, go with the flow. So this is go with the flow, and so the magnetic field goes with the flow, or put the other way around, the gas goes with the magnetic field. So if you imagine that as representing some gas, and we put it on a magnetic field line like that, then it will just move with the magnetic field lines. Or I can think about that as the gas that's moving and carrying the magnetic field with it. The gas can move along the magnetic field, but perpendicular it has to move like that. So that is go with the flow. The tension, that's another self-help principle, I believe, push-pull. Okay, so let us now, what do we got now? Move on. So this is go with the flow and push-pull. So you can see them there. Now, again, this is an image of the sun, which I think is again. Oh, that was moving, okay. Okay, so I don't know how that one worked and the others didn't, but okay, you can see loops of magnetic field there, and there. One of the things about them is, and this is something that you can see here like this, is that when you have these loops of magnetic field and you twist them, then you make electrical currents flow along them. So electrical currents flows along the magnetic field, and you can see that when you twist them too much, something like that can happen. Okay, and those sort of instabilities are present in these images of the magnetic fields on the sun, and the same thing can happen on accretion disks. So let's just move on. Whoops, where's my slide advancer here? So move on. Now what I want you to imagine is some magnetic field lines that are frozen into or going with the flow of the orbiting gas in the accretion disk orbiting the black hole there. So I've got another demonstration here. I've got an accretion disk like that. I've got some magnetic field lines in like that. I've got some gas like that. And some gas like that. So I've got gas, a magnetic, oh, I forgot one thing. I forgot the black hole. So no expense has been spared in this demonstration. So if I have gas and magnetic field, and I orbit like that, so this is an orbiting accretion disk. You never thought you'd see a real-time demonstration. Don't come too close. Okay, nothing happens. Now, let's incline those magnetic field lines like that, outwards. Okay, now I'm going to spin around. Okay, so what we see there is if we incline those magnetic field lines outwards, ooh, that's better. We incline those magnetic field lines outwards, the gas goes out. It is flung out from the disk. It makes an outflow. But it is carrying the magnetic field with it. So if we have the magnetic field like this, then the gas is going to orbit around like, the disk is going to orbit like that. The magnetic field line is going to go back. The inertia is going to pull it around. And then the magnetic field is going to look like that. And the tension along these magnetic field lines is going to do what those bands did on the balloon. It's going to squeeze the gas towards the axis. Obviously, there's a lot more going on here, but that is the essence of what is going on, and that is one way of making a collimated outflow. Now let's carry this story forward to the black hole. The gas itself in the orbiting accretion disk is orbiting very fast, and this is a very good conductor. And it carries the magnetic field with it. The black hole, by contrast, is a rather poor electrical conductor. It is an okay electrical conductor, but not very great. It has a resistance, for those of you who know Ohm's law, of about 100 ohms. So a black hole has a resistance of about 100 ohms, which means it's a sort of middling conductor. So what that means is that if we take these magnetic field lines and we sort of twist it around, they will slip with respect to the surface of the black hole, the event horizon, if you like, but they will still twist up. And that twisting up will do the same sort of trick as happened with the accretion disk, and it will collimate the electromagnetic power coming from the black hole into a jet. And so essentially we have an electromagnetic generator here, like a Faraday disk. It makes a voltage, in the case of a quasar, of about 10 to the 20 volts. So if you know what a megavolt is, that's 10 to the 6 volts. You know what a teravolt is, that's 10 to the 12 volts. This is 10 to the 20 volts. That is a lot of voltage. It makes huge currents too, and those power the jets that we see, and the gas here is of course very, very much evacuated, and we do not have the gas is very evacuated, so there's not a lot of plasma around, and it turns out under those circumstances we can make a lot of charged particles of very high energies, and they can radiate the gamma rays and the radio waves that we see. So here, just let me make that point a little more clearly here. If you're doing the spinning black hole, this is what we have here, is an accretion disk which gets a bit thick in the middle. There's the black hole there. Here are the magnetic field lines twisting around like this, and they're making this electromagnetic energy flux there. Now, what we have here is not a cartoon, but it is a numerical simulation which shows this process at work. And you'll see two views of a faithful computer simulation using the principles of magnetohydrodynamics. And you'll see that starting off from zero, the jet forming there, looking from the side, and you can see it moving from side to side and then looking above. And we've learned a lot about how these structures behave from these simulations, and by analyzing these simulations, comparing them with the increasingly detailed observations, we're starting to produce a picture of how black holes can energize the jets and much of the other activity. In fact, one of the things that's really rather interesting that has come up recently, you may remember I said in the Spherical galaxies, the source of the energization was above the black hole. Let's say, let's put the black hole there. No, let's do this one here. So here's the black hole there, okay? So above the black hole was where the source of the energization was. If we imagine a little loop of field like this to start off with, and then because of the differential rotation, that part there will advance with this will move a little bit like that, and that'll move further there, then further there, and further there, and further there. Now if we imagine two loops of field, then very quickly we're going to get a sort of tangling on the axis, and that's where all the energization is going to happen. And that might be an explanation for why the Spherical galaxies seem to be illuminated from above the black hole. It is the tangling of loops of field above the axis. Let me say a little bit more about the tangling of field. This is terribly important because it may well be a source of all the gamma rays and the radio waves that we see. If we have loops of field, imagine two magnetic field lines like that, could possibly come and help. And Arne, could you help too? I want to show one more process that is terribly important. And so that is that end there, and you're going to hold that there, one each like that. And this is a process known as reconnection. And so imagine two magnetic field lines. This one is going that way, that one is going that way. And then if we bring them together like that, then it is possible just in a very small region in the middle here like this to have them exchange partners like this and like that. Whoops, sorry, I did that the wrong way around. Sorry, like that and like that. And they move apart like that. So this is what Jascha Ardeberg would recognize, thank you very much, as being able to resolve some knot like that, because we would allow the reconnection of the field lines across that knot. And this is something that has to happen, because if we imagine twisting up all these magnetic field lines, they will very quickly become very tangled. And I've performed another computer simulation of the tangling of magnetic field lines, in fact, I perform this every day, is if you go off to work like this. Oh, that was, okay, I'm reconnected. Okay, so here we go. So you may perform this experiment too. And so magnetic field very easily does that. And sometimes it can reconnect in the way we just showed in that demonstration. But sometimes it can do things like this. There is a slip knot like that. And if we do that, that is a very dramatic rearrangement, and that could be responsible for an awful lot of the big flares that we see. So there is a difference between, if you like, the topology changing magnetic field configurations and the ones that are going to preserve the topology can happen much faster. Okay, so we have that little simulation there. Let's just go forward now, I think. So you may say, why did I show that? Well, I was going back to my motif of the locomotive, and I used to think about these radio jets and so on as exhausts or smoke from the engine, but now I think about them more as the Hyperloop, highly evacuated straight channels that are powered by electromagnetic propulsion and move at immense speeds, almost as fast as the signal speed that they can have. So this may be now it isn't a steam locomotive, it isn't an electrical locomotive, it is the locomotive perhaps of the future, the Hyperloop. So just to quickly finish up, there is much that is happening in the future here. I'll be very quick about this. There is neutrino astronomy. It has just begun. There are 100 extragalactic neutrinos that have been seen. We don't know where they come from, but a prime source is an active galactic nucleus. There is high-energy cosmic ray astronomy, seen here in Auger. The first facility was in the South Pole. This is in Argentina, the Auger facility. They measure cosmic rays with energies of 10 to the 20 electron volts. Clearly, an active galactic nucleus is a prime possible origin for that. For those who are confused about the energy of 10 to the 20 electron volts, that's somebody you may know. And he kicks a soccer ball. That has an energy of 10 to the 20 electron volts, but it's in a proton in our case. Okay. This is going to be this is a let me move on quick. I haven't got time to quite explain that one. So this one is, well, actually I will. This is a gamma high. The one before was a high energy gamma ray facility that is coming, and this is very long baseline interferometry, which is going to use the South Pole, which has the capability of imaging the flow around the black hole. This is called the Event Horizon Telescope. Within a few years, it is hoped that we'll be able to make very crude images on the scale of the black hole. And here is gravitational radiation, the future, a spaceborne observatory called LISA, which we hope is going to be deployed perhaps within, it may take a couple of decades, but this will be, see massive black holes and the gravitational waves like those already seen by LIGO, but from the massive black holes. So let me just finish now. I'd like to do this by quoting Leo Tolstoy again. And let me abridge his critique of the great man theory of history. I have to abridge it because War and Peace is rather long. The life of nations is not contained in the lives of a few men, for the connection between those men and the nations has not been found. The theory that this connection is based on the transference of the collective will of a people to a certain historical personage is an hypothesis unconfirmed by the experience of history. For this is like watching the movement of a herd of cattle and paying no attention to the varying quality of the pasturage in different parts of the field, and attributing the direction that the herd takes to what animal happens to be at its head. Personally, I can only half agree with Tolstoy when it comes to science. In the theory of black holes, singular discoveries were made by singular individuals, by Albert Einstein, who gave us the governing concepts and equations, by Karl Schwarzschild, who solved them so that they could be described static black holes, and by Roy Kerr, who did the same for rotating black holes. For my part, I feel fortunate to have lived at a time when so much enduring discovery has been made and continues to be made. And I'm just so lucky to be able to belong to the community and have so many wonderful collaborators over the years. Some of these are my teachers, some are my colleagues, some are my postdocs, and some are my students. And there are also some members of my family embedded in this montage. This is my herd. I feel privileged to have worked with them on a common quest to understand black holes and active galaxies, and I offer them my sincere thanks for their good fellowship and for teaching me so much. And thank you once again for the award of a Crafoord Prize in Astronomy. I'm honored to receive it.